The B12 intrinsic factor binds to cubulin and is taken in an endosome. The endosome fuses with lysosome to release B12. So the intrinsic factor gets degraded, the cubulin is recycled for use later. That's not as important to me as the other stuff.
Professor
Right.
Thayer,
Yes.
one more time, a little
Yeah,
slower,
no problem.
please.
Okay, so let me get rid of this. Okay, so let me make sure I didn't miss anything that I put in here that I want. No, okay.
And why does it need a binding protein?
Okay, so it's not, this thing likes to bind to protein. Okay, this is conjecture based on evolutionary history. In other words, I don't know that I know the real reason that it needs to, but cyanocobalamin is bound to proteins when we take it in, right? So when we go into the stomach, the low pH starts degrading the protein, right? That's where we start active protein digestion. So that process releases the B12. We don't complete the protein digestion process there, we just start it. So it's my opinion that if we did not bind it to an R binding protein, I don't know why they call it R, but if we did not bind it to a specific binding protein, it would just get bound to another protein and go down through the small intestine and we wouldn't be able to access it. That's my evolutionary opinion on why this process has evolved, because it protects it from going out. In other words, we cannot really, unlike other B vitamins, we can't really diffuse this one. And so, but we really, really need it, and it so sticks to proteins, and we don't always digest all of our proteins. So this mechanism, as I'll go through the steps one more time, really protects our ability to take it in. Because otherwise it could just find another protein that we didn't digest and just go out with it. Okay, so food goes into, it's not a perfect system, by the way. We're going to do that next. Food goes into the stomach. Vitamin B12 is released from the protein in the food it's bound to. Vitamin B12 binds to an R protein and travels to the small intestine, so that when it's bound, it's protected from binding to another protein, or it's protected from damage or other things. In the small intestine, so we've changed two things. One, we've changed the pH, and two, we've added these proteasomes, or, well, not proteasome, proteolytic enzymes, the breakdowns of the enzymes which break down protein in the lumen of the small intestine. We're in the duodenum. They're released from the pancreas, right? So they release B12 from the R-binding protein because that protein gets broken down by these enzymes, so B12 pops off. So now we've got free B12 again. But again, now B12 is free to hop onto any other protein it can find. So instead, B12 attaches to the intrinsic factor, which is also produced by the stomach, but ends up in the small intestine. Okay, so this complex, this B12 intrinsic factor complex, travels to the distal ileum. So it goes all the way through from up here, all the way down to the bottom. So do you guys remember a long time ago, we talked about the ileal brake? Have you guys heard about the ileal brake concept? Okay, so there is a mechanism in the distal ileum whereby there's a sensing mechanism which has the ability, it's not like a brain exactly, but there are a series of chemosensors and judges of enzymatic activity that determine how much nutrition has been absorbed from the food up to that point. If it is judged not by a processing brain, but by a series of chemical sensing cells that send messages to up or down regulate certain things, if it's sensed that we haven't taken enough nutrition out of that food, we activate the ileal brake, which slows the entire digestive process down and lets that food sit for longer so that the enzymes have more time to break down the food. So, and that's the ileal brake. So I'm thinking, if you get all the way down here to the ileal brake, the distal ileum, then you can work in concert with the ileal brake to make sure that this comes in. Again, that's me knowing the evolutionary history and a bunch of stuff about anatomy and physiology, but that's not being sure. That's just me putting the pieces together and taking my best guess as to why it evolved this way, because we really need this, and we can only get it from certain things. Okay, so we bind to the intrinsic factor, we travel to the distal ileum. In the distal ileum, the cubulin, which is the protein, binds to the AMN, which is the other protein. So this is our receptor protein, right? And travels to the enterocyte surface. So here's cubulin. Here comes our B12 intrinsic factor, and it sticks. And then we make our endosome and pull it into the cell. It binds to the cubulin, and it's taken in via endosome. And then the endosome fuses with the lysosome and releases B12. And then we have B12 in the middle of the intestine. Okay, so going back to evolution.